In quantum physics, quantum state refers to the state of a quantum system. A quantum state can be either pure or mixed. A pure quantum state corresponds to a vector, called a state vector, in a Hilbert space. For example, when dealing with the energy spectrum of the electron in a hydrogen atom, the relevant state vectors are identified by the principal quantum number written. For a more complicated case, consider Bohm's formulation of the EPR experiment, where the state vector involves superposition of joint spin states for two particles. Mathematically, a pure quantum state corresponds to a state vector in a Hilbert space over complex numbers, which is a generalization of our more usual three-dimensional space. If this Hilbert space is represented as a function space, then its elements are called wave functions. A mixed quantum state corresponds to a probabilistic mixture of pure states. However, different distributions of pure states can generate equivalent mixed states. Mixed states are described by so-called density matrices. A pure state can also be recast as a density matrix. In this way, pure states can be represented as a subset of the more general mixed states. For example, if the spin of an electron is measured in any direction, e.g., with a Stern-Gerlach experiment, there are two possible results, up or down. The Hilbert space for the electron's spin is therefore two-dimensional. A mixed state, in this case, is a matrix that is Hermitian, positive definite, and has trace 1. Before a particular measurement is performed on a quantum system, the theory usually gives only a probability distribution for the outcome, and the form that this distribution takes is completely determined by the quantum state and the observable describing the measurement. These probability distributions arise for both mixed states and pure states. It is impossible in quantum mechanics to prepare a state in which all properties of the system are fixed and certain. This is exemplified by the uncertainty principle, and reflects a core difference between classical and quantum physics. Even in quantum theory, however, for every observable there are some states that have an exact and determined value for that observable. Conceptual description. Pure states in the mathematical formulation of quantum mechanics. Pure quantum states correspond to vectors in a Hilbert space, while each observable quantity is associated with a mathematical operator. The operator serves as a linear function which acts on the states of the system. The eigenvalues of the operator correspond to the possible values of the observable, i.e., it is possible to observe a particle with a momentum of 1 kg/meter per second if and only if one of the eigenvalues of the momentum operator is 1 kg/meter per second. The corresponding eigenvector with eigenvalue 1 kg/meter per second would be a quantum state with a definite, well-defined value of momentum of 1 kg/meter per second, with no quantum uncertainty. If its momentum were measured, the result is guaranteed to be 1 kg/meter per second. On the other hand, a system in a linear combination of multiple different eigenstates does in general have quantum uncertainty for the given observable. We can represent this linear combination of eigenstates as the coefficient which corresponds to a particular state in the linear combination is complex, thus allowing interference effects between states. The coefficients are time-dependent. How a quantum system changes in time is governed by the time evolution operator. The symbols and surrounding the are part of Ket notation. Statistical mixtures of states are different from a linear combination. A statistical mixture of states is a statistical ensemble of independent systems. Statistical mixtures represent the degree of knowledge, whilst the uncertainty within quantum mechanics is fundamental. Mathematically, a statistical mixture is not a combination using complex coefficients, but rather a combination using real-valued, positive probabilities of different states. A number represents the probability of a randomly selected system being in the state. Unlike the linear combination case, each system is in a definite eigenstate. The expectation value of an observable A is a statistical mean of measured values of the observable. It is this mean, and the distribution of probabilities, that is predicted by physical theories. There is no state which is simultaneously an eigenstate for all observables. For example, we cannot prepare a state such that both the position measurement Q and the momentum measurement P are known exactly. At least one of them will have a range of possible values. This is the content of the Heisenberg uncertainty relation. Moreover, in contrast to classical mechanics, it is unavoidable that performing a measurement on the system generally changes its state. More precisely, after measuring an observable A, the system will be in an eigenstate of A, thus the state has changed, unless the system was already in that eigenstate. This expresses a kind of logical consistency. If we measure A twice in the same run of the experiment, the measurements being directly consecutive in time, then they will produce the same results. This has some strange consequences, however, as follows. Consider two incompatible observables, A and B, where A corresponds to a measurement earlier in time than B. Suppose that the system is in an eigenstate of B at the experiment's begin. If we measure only B, all runs of the experiment will yield the same result. If we measure first A and then B in the same run of the experiment, the system will transfer to an eigenstate of A after the first measurement, and we will generally notice that the results of B are statistical. Thus, quantum mechanical measurements influence one another, and it is important in which order they are performed. Another feature of quantum states becomes relevant if we consider a physical system that consists of multiple subsystems, for example, an experiment with two particles rather than one. Quantum physics allows for certain states, called entangled states, that show certain statistical correlations between measurements on the two particles which cannot be explained by classical theory. For details, see entanglement. These entangled states lead to experimentally testable properties that allow us to distinguish between quantum theory and alternative classical models. Schrodinger picture versus Heisenberg picture. One can take the observables to be dependent on time, while the state sigma was fixed once at the beginning of the experiment. This approach is called the Heisenberg picture. Conceptually, the two approaches are equivalent. Choosing one of them is a matter of convention. Both viewpoints are used in quantum theory. While non-relativistic quantum mechanics is usually formulated in terms of the Schrodinger picture, the Heisenberg picture is often preferred in a relativistic context, that is, for quantum field theory. Compare with Dirac picture. Formalism in quantum physics. Pure states as rays in a Hilbert space. Quantum physics is most commonly formulated in terms of linear algebra, as follows. Any given system is identified with some finite or infinite-dimensional Hilbert space. The pure states correspond to vectors of norm 1. Thus the set of all pure states corresponds to the unit sphere in the Hilbert space. Multiplying a pure state by a scalar is physically inconsequential. If one vector is obtained from the other by multiplying by a scalar of unit magnitude, the two vectors are said to correspond to the same ray in Hilbert space and also to the same point in the projective Hilbert space. Ket notation calculations in quantum mechanics make frequent use of linear operators, scalar products, dual spaces and Hermitian conjugation. In order to make such calculations flow smoothly, and to obviate the need to fully understand the underlying linear algebra, Paul Dirac invented a notation to describe quantum states, known as Ket notation. Although the details of this are beyond the scope of this article, some consequences of this are: the expression used to denote a state vector takes the form. This can be contrasted with the usual mathematical notation, where vectors are usually bold, lowercase letters, or letters with arrows on top. Dirac defined two kinds of vector, Bra and Ket, dual to each other. Each Ket is uniquely associated with a so-called Bra, denoted, which corresponds to the same physical quantum state. Technically, the Bra is the adjoint of the Ket. It is an element of the dual space, and related to the Ket by the Riesz representation theorem. In a finite-dimensional space with a chosen basis, writing as a column vector is a row vector. To obtain it, just take the transpose and entry-wise complex conjugative. Scalar products are written so as to look like Hebra and Ket next to each other. Spin. The angular momentum has the same dimension as the Planck constant and, at quantum scale, behaves as a discrete degree of freedom. Most particles possess a kind of intrinsic angular momentum that does not appear at all in classical mechanics and arises from Dirac's relativistic generalization of the theory. Mathematically, it is described with spinors. In non-relativistic quantum mechanics, the group representations of the Lie groups are used to describe this additional freedom. For a given particle, the choice of representation is specified by a non-negative number s that, in units of Planck's reduced constant h, is either an integer or a half-integer. For a massive particle with spin s, its spin quantum number m always assumes one of the two s plus 1 possible values in the set as a consequence. The quantum state of a particle with spin is described by a vector-valued wave function with values in C2s plus 1. Equivalently, it is represented by a complex-valued function of 4 variables. One discrete quantum number variable is added to the usual 3 continuous variables. Many body states and particle statistics. The quantum state of a system of n particles, each potentially with spin, is described by a complex-valued function with 4 variables per particle, e.g., here, the spin variables mu assume values from the set where is the spin of nu th particle. For a particle that does not exhibit spin, the treatment of identical particles is very different for bosons versus fermions. The above n-particle function must either be symmetrized or anti-symmetrized with respect to the particle numbers. If not all n-particles are identical, but some of them are, then the function must be symmetrized separately over the variables corresponding to each group of identical variables, according to its statistics. Electrons are fermions with s equals 1/2, photons are bosons with s equals 1. When symmetrization or anti-symmetrization is unnecessary, n-particle spaces of states can be obtained simply by tensor products of one-particle spaces, to which we will return later. Basis states of one-particle systems. As with any Hilbert space, if a basis is chosen for the Hilbert space of a system, then any Ket can be expanded as a linear combination of those basis elements. Symbolically, given basis Kets, any Ket can be written where Ci are complex numbers. In physical terms, this is described by saying that has been expressed as a quantum superposition of the states. If the basis Kets are chosen to be orthonormal, then one property worth noting is that the normalized states are characterized by and for orthonormal basis. This translates to expansions of this sort play an important role in measurement in quantum mechanics. In particular, if the eigenstates of an observable, and that observable is measured on the normalized state, then the probability that the result of the measurement is key is Ci. A particularly important example is the position basis, which is the basis consisting of eigenstates with eigenvalues of the observable, which corresponds to measuring position. If these eigenstates are non-degenerate, then any Ket is associated with a complex-valued function of three-dimensional space. This function is called the wave function corresponding to. Similarly to the discrete case above, the probability density of the particle being found at position as and the normalized states have, in terms of the continuous set of position basis, the state is superposition of pure states. One aspect of quantum states, mentioned above, is that superpositions of them can be formed if and are two Kets corresponding to quantum states. The Ket is a different quantum state. Note that which quantum state it is depends on both the amplitudes and phases of an. In other words, for example, even though and correspond to the same physical quantum state, they are not interchangeable, since for example and do not correspond to the same physical state. however, and do correspond to the same physical state. This is sometimes described by saying that global phase factors are unphysical, but relative phase factors are physical and important. One example of a quantum interference phenomenon that arises from superposition is the double slit experiment. The photon state is a superposition of two different states, one of which corresponds to the photon having passed through the left slit, and the other corresponding to passage through the right slit. The relative phase of those two states has a value which depends on the distance from each of the two slits. Depending on what that phase is, the interference is constructive at some locations and destructive in others, creating the interference pattern. By the analogy with coherence in other wave phenomena, a superposed state can be referred to as a coherent superposition. Another example of the importance of relative phase in quantum superposition is Rabi oscillations, where the relative phase of two states varies in time due to the Schrodinger equation. The resulting superposition ends up oscillating back and forth between two different states. Mixed states. A pure quantum state is a state which can be described by a single Ket vector, as described above. A mixed quantum state is a statistical ensemble of pure states. Mixed states inevitably arise from pure states when, for a composite quantum system with an entangled state on it, the part is inaccessible to the observer. The state of the part is expressed then as the partial trace over. A mixed state cannot be described as a Ket vector. Instead, it is described by its associated density matrix, usually denoted ρ. Note that density matrices can describe both mixed and pure states, treating them on the same footing. Moreover, a mixed quantum state on a given quantum system described by a Hilbert space can be always represented as the partial trace of a pure quantum state on a larger bipartite system for a sufficiently large Hilbert space. The density matrix describing a mixed state is defined to be an operator of the form whereas the fraction of the ensemble in each pure state. The density matrix can be thought of as a way of using the one-particle formalism to describe the behavior of many similar particles by giving a probability distribution of states that these particles can be found in. A simple criterion for checking whether a density matrix is describing a pure or mixed state is that the trace of ρ2 is equal to 1 if the state is pure, and less than 1 if the state is mixed. Another, equivalent, criterion is that the von Neumann entropy is 0 for a pure state, and strictly positive for a mixed state. The rules for measurement in quantum mechanics are particularly simple to state in terms of density matrices. For example, the ensemble average of a measurement corresponding to an observable A is given by where eigenkits and eigenvalues, respectively, for the operator A, and TR denotes trace. It is important to note that two types of averaging are occurring, one being a weighted quantum superposition over the basis kets of the pure states, and the other being a statistical average with the probabilities PS of those states. According to Wiener, the concept of mixture was put forward by Landau. Interpretation. Although theoretically, for a given quantum system, a state vector provides the full information about its evolution, it is not easy to understand what information about the real world it carries. Due to the uncertainty principle, a state, even if it has the value of one observable exactly defined, cannot exactly define values of all observables. For state vectors, probability amplitudes offer a probabilistic interpretation. It can be generalized for all states, for instance, as expectation values mentioned above. Mathematical generalizations. States can be formulated in terms of observables, rather than as vectors in a vector space. These are positive normalized linear functionals on AC** algebra, or sometimes other classes of algebras of observables. See state on AC** algebra and Gelfand-Naimark-Siegel construction for more details. Consider Bohm's formulation of the EPR experiment, where the state vector involves superposition of joint spin states for two particles. Mathematically, a pure quantum state corresponds to a state vector in a Hilbert space over complex numbers, which is a generalization of our more usual three-dimensional space. If this Hilbert space is represented as a function space, then its elements are called wave function, gives only a probability distribution for the outcome, and the form that this distribution takes is completely determined by the quantum state and the observable describing the measurement. These probability distributions arise for both mixed states and pure states. It is impossible in quantum mechanics to prepare a state in which all properties of the system are fixed and certain. This is exemplified by the uncertainty principle, and in quantum physics, quantum state refers to the state of a quantum system. A quantum state can be either pure or mixed. A pure quantum state corresponds to a vector, called a state vector, in a Hilbert space. For example, when dealing with the energy spectrum of the electron in a hydrogen atom, the relevant state vectors are identified by the principal quantum number, written. For a more complicated case, example, if the spin of an electron is measured in any direction, e.g., with the Stern-Gerlach experiment, there are two possible results, up or down. The Hilbert space for the electron's spin is therefore two-dimensional. A mixed state, in this case, is a matrix that is Hermitian, positive definite, and has trace 1. Before a particular measurement is performed on a quantum system, the theory usually functions. A mixed quantum state corresponds to a probabilistic mixture of pure states. However, different distributions of pure states can generate equivalent mixed states. Mixed states are described by so-called density matrices. A pure state can also be recast as a density matrix. In this way, pure states can be represented as a subset of the more general mixed states. For example,